This is CS797K. It is Wednesday, January 29th. It's Curmudgeon's Day. So if you know a curmudgeon, say hello to the curmudgeon. It's also Kansas Day, but no one cares. Okay, so today's lecture is on Hamming code and parity. You remember we did the parity trick before. We laid out the cards, and we were able to tell which card had turned over because we had parity in two different directions. But we had a lot of extra cards we laid out. And so our question is, we start getting into this, we start asking ourselves, how can we efficiently have redundancy in our data such that as we're transmitting the data, if errors creep in as we're transmitting it, how can we reconstruct the correct data on the other end, right? And how can we do that without too much overhead, right? And so as we get into this class later, we're going to discuss the idea of information theory, which was pioneered by a fellow named Claude Shannon. He came up with the idea that you can actually have measurable ways to tell how much information is coded in your message and how much extra information you need to add to be able to protect and recover from arbitrary numbers of errors in the code. Again, on our course outline, we're in the data storage part. We're doing basic parity bit protection, or just starting into our lectures here, Hamming code. We'll get into the other things later. We need to take the animations off of that. So code is a linear error correcting code. In other words, as you're sending the data, think of the data as a stream of bits, ones and zeros running down a pipeline, right? As you're sending that, the data is in line. It's linear. It's also a block code because it takes the data, it adds the information in there, kind of takes your data as a pipeline, spreads it out, makes a longer line, adds in parity bits, and then ships it off down your transmission line, right? So one block at a time. There are linear error correcting codes that are stream codes that are actually adding extra parity information as it's going through the pipeline, and can work with arbitrary sizes, right? Hamming code can work with arbitrary sizes, but you need to know what it is first. How long is my data that I'm going to encode with a Hamming code? It was invented way back in 1950 by someone named Hamming, amazingly enough. And they were using punch card readers. They had those little, pieces of, manila colored paper that they'd punch holes in there to put the data in there. They didn't have, iPhones back in 1950, right? And their punch card reader kept jamming and reporting errors and things like that. And so the guy was getting annoyed with that. And he says, can I come up with some way that I can encode the data on this card so that if some small thing goes wrong and one of the bits gets wrong, when it didn't completely punch the hole out, it was called a hanging chad for some reason. And the idea was that the hole could close up again and the bit was wrong, right? And so he wanted to come up with a way to be able to reconstruct those and fix them. So he developed the Hamming code, and he wrote a scholarly paper about it, and that was the basis of error detection and recovery. So the original that he published for illustration purposes was called the Hamming 7.4 code. Hamming 7.4 code can detect and correct single bit errors. It can detect double bit errors, but it cannot correct them. It fails to detect triple bit errors. You remember when we did our card trick, our parity trick, right? If you flipped over one card, we could tell which one it was and fix it. If we flipped over two cards, we could tell that two cards had been flipped over, but we didn't know how to fix it correctly, right? And if we were to flip over three cards, we could have made it look like it was perfectly correct, right? Just with the wrong code. So this is a Hamming distance of 3. We'll talk about what a Hamming distance is in a little bit, or an edit distance. Hamming 7.4. The 7 means that's how many bits are in your encoded message. The 4 means how many data bits are in that message. So basically, we're going to take 4 bits of data, one single hexadecimal number, and we can encode that using 7 bits, right? And so there are 3 parity bits, obviously 7 minus 4. This is a coincidence. The Hamming distance is what's known as the or the edit distance, is a metric that says how many symbols do I have to change, how many bits do I have to flip to change from one valid symbol to another, right? The number of parity bits is simply how many parity bits are in the message. As we get bigger and bigger messages, we'll see that the Hamming distance could stay 3, and the number of parity bits could go 4, 5, 6, 7, 8, 9, whatever, right? It's the way that you code the message that defines how long the edit distance is. So edit distance, or Hamming distance, is given a set of strings or symbols. How many changes do you need to turn one string into another, right? How many errors do you introduce in your message before you interpret it as the wrong data, right? How many changes you need to turn one string into another? Hamming distance is one edit distance. Another edit distance called Levenshtein distance. Another distance called longest common sequence, or LCS. There's also the Damerau-Levenshtein distance and the Jarrow distance. And each of these measures different things. Hamming distance is developed by, what was his name, Hamming, only changes substitutions, right? Levenshtein distance measures substitutions plus insertions and deletions. So you can see that Hamming distance will only work for equal length strings, right? How many bits can I flip to turn this string into this other one, right? You can make it look like you're dealing with different length strings if you have spaces, but the spaces are still there, right? Levenshtein distance, again, you can make your string longer, shorter, and you can get a metric that says how far apart two things are. LCS measures only insertions and deletions. Obviously, one insertion plus one deletion at the same place is a substitution, right? So this is just a slightly different way to count a substitution, but it can also handle insertions and deletions. Damerau-Levenshtein distance metric, again, counts all of the above, including transpositions. If you switch two letters in the middle, right? And this is like used for like spelling checkers. You know, if you type in a word and you switch two letters accidentally, it turns out to be a very common thing. And so there are actually spell checkers will go out there and measure the transposition distance. And Jarrow distance, of course, only measures transpositions, right? So this is a thing that was, Jarrow distance was developed specifically for spelling checkers, right? So the Hamming distance is the minimum number of substitutions required to change one string to another equal length valid string. If we have two words, names, Carolyn and Catherine, right? In order to change one to the other, we have to change the R to a T. We have to change the O to an H. We have to change the L to an R. So the Hamming distance on those two strings is 3, right? In binary, the Hamming distance is the minimum number of bit flips to change one valid code to another. Back up briefly. LCS and Levenshtein measure substitutions. Levenshtein measures substitutions, insertions, and deletions, right? What is the Levenshtein distance from Carolyn to Catherine? And the answer is, well, we could have it as 3 flips, right? Or we could have 2 deletions. Just delete the O in the, or delete the O and the L, right? And then add a T and H in front of the R, but it's still longer, right? So the Levenshtein distance is still 3 because its substitutions are more efficient than deletion reinsertion in this case. In other cases, deletion reinsertion is more efficient than a substitution, right? So in binary, we look at the ASCII letter A, capital A, hexadecimal code is hex 41. In binary, it's 01000001. Lowercase a is 01100001 or hexadecimal 61. So you can see by flipping a single bit, we've changed one valid symbol to another valid symbol. So there's not any redundancy to protect you in ASCII, right? If you get something is inserting errors into your transmission, you can't tell a difference, right? Of course, other codes, Levenshtein, Jarrow measure insertions, deletions, transpositions. Again, I said the LCS distance, only do insertions and deletions, is 4. Levenshtein is 3. And in coding with Hamming distance D, can detect D-1 errors. We'll call this E, the number of errors we can detect, okay? E errors can be detected if E is strictly less than D. straightforward. It can correct d minus 1 over 2. That is E floor division of 2. So Hamming distance of 1 can detect how many errors? 0. How many can it correct? 0. Hamming distance of 2 can detect 1 error, but it can't correct any, right? It's only when you get to Hamming distance of 2 or 3 that you can detect 2 errors and correct 1. Okay, so just to see if you're awake, how many errors can we detect here? 3. How many can we correct? Still 1. Yeah, you divide 3 by 2, you get 1.5. Hamming distance of 5 can detect 4 errors. How many can it correct? 2. Right, so the more you add in for redundancy, the further your Hamming distance, edit distance is, the more errors you can correct. Hamming distance of 1, of course, was really? Do I say that? Yeah, okay. Again, Hamming distance 1, ASCII, hex 41, hex 61, only a single bit change, so the Hamming distance is 1. In fact, character C, 1000011, is also a single bit flip. And capital E, capital I, all sorts of other letters are just a single bit flip away from that capital A. So it's not very good. But originally, ASCII was developed with a Hamming distance of 2. It just wasn't all that useful to have a Hamming distance of 2. So when ASCII was first designed back in the 1960s, I think, it was actually listed as a 7-bit code. And that top bit was a parity bit. So by adding 1 parity bit in our stream, we change our Hamming distance from 1 to 2. And again, we just make it even parity, right? So A, capital A is 0100, lowercase 1100, 11000001. Too many A's. Anyhow, so we had 2 bits change. So if you flip a single bit, you know you're not going to have a valid symbol. You can tell there was an error in transmission. Unfortunately, people needed more letters, and so they tossed that parity bit out. Hamming distance of 3. Can we just add a second parity bit? No, because that second parity bit provides no more useful information, right? If we just add another parity bit up here on the front, it would just be a 0, because we've already set 1 parity bit. What we have to do is we have to add parities on the pieces of the data. So if we break it into 2 dimensions, there's our capital A, 01000001, right? So we broke it into a 2 by 4. And now we make in both directions the parity even. So we've got 1, 2, 3, 4, 5, 6 parity bits. And if this starts to look like the parity card trick, that's because it is, right? Now, if we have a single bit flip, we can see there's 2 odd parities and we can correct it. 2 odds. If we, and correct it. If we have 2-bit flips, we can detect it, but we might correct it wrong. In this case, we'll look at this and say, well, this is even, or yeah, and this is odd. And so we only have an odd here, so it must be the parity bit itself must have got flipped. So we're going to incorrectly change that parity bit to make it look like that was the error, right? So 2-bit flip detectable, corrects wrong. 3-bit flip, undetectable. We don't know, you know, it might not be. Depending on where the bit flips are, we might still detect there's an error, but it might also be just completely clean other symbol. And again, this is saying lowercase a, right? So Hamming distance of 4. In this table we just made, we have 6 parity bits. Each covers a portion of the data. If we add an overall parity bit in the corner, now this parity bit checks the parity bits we just added, right? So, and this is literally the parity magic trick that we did. Hamming distance is now 4. Why? Again, we can have a 3-bit flip is detectable. We can see there's an odd number here, an odd number here, right? So we know that there is an error. We will, of course, correct it wrong because this says even, this says even, this says even, even, even. So we would actually go out there and flip that bit. We detected there was an error, but we corrected it wrong. Okay. A 2-bit flip is detectable and uncorrectable, but it knows that 2 bits are wrong. Again, Hamming distance of 4. We can detect 3 errors. 3 divided by 2 is 1.5, so we can only correct 1 error successfully. So a single bit flip like that remains easily correctable. And can we get into higher Hamming distances? Yes, we'll see that later on. So review, Hamming 7,4, the original Hamming code, which we could also refer to as 7,4,3, where this last 3 is not the number of parity bits, but is the Hamming distance, right? 7 bits in the message, 4 bits of data, 3 bits of parity, 7 minus 4, and the Hamming distance itself is 3. Our 2-dimensional parity that we just designed is the same Hamming distance. It has 8 data bits and 7 parity bits. So we would call that a Hamming distance of 15,8,4 if we're going to write down the Hamming metric, distance metric for that coding, right? So that's not very efficient. What did Richard Hamming do? He devised an efficient way to code Hamming distance 3 and 4 protection with a minimum number of parity bits. How does it work? Well, sorry, no, we're not there yet. Hamming 8,4,4. Hamming was working in the 1950s. We hadn't yet decided that all computers should start at 0. So the Hamming code starts at bit 1, 2, 3, 4, 5, 6, and 7, right? Well, he added a bit 0 later on, or as he was finished with the illustrative part of his paper, right? By adding an overall parity bit, that increases the Hamming distance to 4, and that is now bit 0. So you know what bit you start on differs. When it reliably corrects 1-bit flip, reliably identifies a 2-bit flip, does not correct a 2-bit flip though. Is what's called a sec-dead code in computer science and engineering. Single error correction, double error detection. 3-bit flip is detected but may correct wrong. Hamming 1511. You can take 11 data bits and using 4 parity bits, 15 minus 11, you can protect all 11 of those data bits. The Hamming distance is only 3. You have to go to having 16,11, adding another overall parity bit check bit to get the Hamming distance of 4. Hamming 128, 120,4 has 120 data bits, 7 parity bits. You see, the bigger the amount of data we protect, the less parity grows, right? Parity grows like as the logarithm of the number of data bits. And it has an overall check bit, which makes the Hamming distance 4. Hamming 7264 is a truncated 128, 120 code. It is sized to fit 64 bits words. It was widely used up until the 2010s in memory. Modified Hamming codes are still used today in a large number of memory chips in computer products, right? There are other codes that are basically improvements on Hamming codes. There are other codes that are different kinds of codings, but still the Hamming code itself is still in use today. The key, binary. Think about round numbers in base 10. 1, 10, 100, 1,000, 10K, a lakh, right? A million, a crore. I think I got those in the right order, right? In binary, round numbers are 1, 2, 4, 8, 16, and so on. But those are all round numbers. It's just a single bit turned on and everything else is zeros, right? So single bit, we'll call those a single bit numbers, right? So what Hamming did was he treats the message as a stream of numbered bits starting at 1, 2, 3, 4, 5, right? And if he's going to start with the overall parity check bit, he's going to start at bit 0. So Hamming 7.4 starts with 1, 2, 3, 4, 5, 6, 7, and stops. There are 2, 3, 4 data bits and 1, 2, 3 parity bits. Hamming 1511 adds one more bit at the 8s, and then has another 7 bits that follow before it gets to the 16th bit. It spreads the message to use non-round numbered bits. Message 1, message 2, message 3, message 4. Message 5 would go down here, and it uses those round numbered bits as the parity. Again, 1s, parity 2, parity 4. Again, yeah. In a number, the least significant bit is the rightmost one. In Hamming, we look at Hamming codes, it's the leftmost. In a string, the first character is called 0. In Hamming, it's called sometimes 1. So in a Hamming message, we count things left to right. You can find online encoders and decoders for Hamming code. Here's a good one. Decode.fr in France. And we can take our message, tell it what we want to do. If we want to analyze this, for instance, we'll take this string here, 1100, we say encode. And it will give us the result right here, 1100 with Hamming parity added. There's a 7-4 code is 0111100. You can mess around with that link. There are bad Hamming coders out there that will confuse you. The reason being that in order to be more efficient, some computer vendors rearranged the bits so that things line up more evenly on nice word boundaries. And so if you try to use this encoder here or just find a random one, there's a very good probability that you'll get something that will not make sense in the context of this class because it's using a complex, convoluted Hamming code with bits rearranged in random orders. Well, not random, semi-random. So here we're going to go and code the string 1101. Again, if we go out here to this code and we say we're going to code 1101, encode it, and it's going to tell us the output is 1010101. We'll see how that works. Okay, so we pad it out. Parity 1, parity 2, our first one, parity 4, our second one, our 0, and our third one. Okay, so we've spread the message and inserted our unknown parity bits. Now we're going to take all the odd numbered bits, 1, 3, 5, and 7. We're going to add those together, and that will tell us what P1 should be. So we got 3 ones, 1, 2, 3. So since that's an odd number, we want to make it even. So we're going to add 1. We make P1 be 1. We sum the 2's bits, right? So 1, 2, 3. And again, if you look at the number 2, it's this. If you look at the number 3, number 4 does not have the 2 bit on, 5 does not, 6 has the 2's bit on, and 7 has that 2's bit on, this finger, right? So we're going to count this one. Oops, don't click on it. This one, and this one. We add those up, we have 2, so we're going to set a 0 into the 2's place. In the 4's place, we're going to look at these last 3 numbers. We have 101, which is an even number, so we're going to put a 0 there, so we're going to get 1010101. Okay. Hamming 8-4. How do we encode that? Well, we start by encoding Hamming 7-4. Reserve a space at the front for the P0 bit. We count up the total number of ones in our coded message. Whether they're parity or data, doesn't matter. We're going to count all of the ones. 1, 2, we're going to count. Yeah, 1, 2, 3, 4 ones in that message. That means there's an even parity already. So we're going to set P0 so that the overall message has an even parity. If we go down here to our code, encode here with Hamming 7-4, it's 0011000. If we say to encode is to Hamming 8-4, it's going to have, well, it's still got an even number of ones. Yeah, because I need to get a code that doesn't have an even number. But that first number, if I set, maybe this one will do it. There we go. So my message originally was 1110. It's spread out. There's P0 bit is a 1 to make it an overall even parity, parity 1, parity 2, parity 4 in the message. Okay. Boom, back here. So that's coded our Hamming 8, 4. Why is it 8? Because we added one more bit. At the front is bit number 0. Decoding a message. Okay, once we've got this thing encoded, we've added parity on there, right? So now we want to decode. And again, what we've done is every bit that is in a round number position is protecting all of the other bits in the message that have that particular bit turned on, right? So the 2's place is protecting everything at 2, 3, 6, 7, 11, 12, 10, 11, so on and so forth. 10, 11, 10, 11, yeah. So we're going to decode our message. We're going to start by masking off all the even numbered bits. So here's our message. This X I'm putting in there to indicate that that's the P0, the overall check bit. So we're doing a Hamming 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This should be an 11, 16, 11, 15 code here. So the simple basic one, we actually, the parity bits are here at bit 1, 2, 4, and 8. And the message bits are at 3, 5, 6, 7, 9, 10, 11, 12, 13, 14, and 15, all the composite numbers in binary, right? So everything where the 1's bit is turned on, 1, 3, 5, 7, 9, 11, we add all those up. How many do we have? 1, 2, 3, 4. Good. That tells us that none of those bits got messed up in transmission. They all transmitted cleanly. We look at our 2's bits. How many of those do we have? 1, 2, 3, 4, 5, 6. Cool, everything transmitted cleanly, right? As long as that bit says an even parity when we add it up, that tells us that the bits covered by that particular parity bit transmitted without any errors in the message. So once we've verified that our parity is clean, we just chop out the parity bits, 1, 2, 4, and 8. And this was the message that we sent, and we received it. So to decode, all you have to do, if you don't care whether you got errors in the message, just throw away the parity bits. If you care whether you're transmitted cleanly, you count the parity for every one of those parity bits, see if it's a 0. If it's not, you fix it. So here we got this message. Let's flip that bit right there, okay? So if we have an error, and this is bit number 1, 2, 3, 4, 5. 5 is represented as a 101. So what bits are going to protect it? What parity bits are going to have an error? Well, it's going to be parity bit 1 and parity bit 4, because 5 is protected by 1 and 4. So we expect to see an odd parity when we look at our 1's parity. We expect to see an odd parity when we look at our 4's. We expect to see even when we look at 2 and 8. Let's find out. Check the 1's. 1, 2, 3. That one's a 0 instead of a 1. This tells us there's a problem. Okay. We check the 2's. 1, 1, 1, 1, 1, 0, 1, 0. That's even. That bit's okay. None of these bits indicates an error. Now again, Hamming distance is 3. If we flip 3 bits, all bets are off, right? If we're looking for a single bit flip, check the 4's. 1, 0, 1, 1, 0, 1, 1, 0. We got 5 bits here turned on. So that's odd. So that tells us there's a problem. We check the 8's. 1, 0, 1, 0, 0, 1, 1, 0. Even. That's okay. Since we found an error at parity bit 1 and parity bit 4, we add those together. We get 5. And that tells us at bit position 5, 1, 2, 3, 4, 5 is where the error occurred in our transmission. And we just flip that bit and everything's fixed. You with me? Simple. Since I've done this lecture so many times, it's simple for me. I don't know if it's simple for you. I hope it is. Hamming 1611. Again, Hamming 1611, we count up the number of bits in here. It's an even number, so we put a 0 in the front. Makes an even parity for the overall message. And now, of course, it's still the same procedure with a single parity bit flip. But if we have 2 bits flipped, can we figure out what to do with it? Can we recognize that there are 2 bits flipped? Hamming distance is now 4. We should be able to detect that 2 bits are flipped. We can't necessarily correct them right, but we can tell that there's a problem. Let's see. Check the 1s. It comes back as even. Check the 2s. It comes back as even. Check the 4s. It says there's a problem. Check the 8s. It says there's no problem. It comes back even, right? So if we didn't have this overall bit, check bit out here, right? We'd say, well, I only have an error in the 4s bit, so basically my 4s parity bit must have flipped itself. And I would correct it wrong. But because I have the overall parity bit flipped, now count the number of 1s in the total message. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. He says, I've got no problem in the overall parity. That tells me that the number of bits flipped is an even number, right? I could have no bits flipped, everything's fine. I could have 2 bits flipped, right? Which is what I have here. I can have 4 bits flipped, but I can't have 3 or 1 or 5. So because I see an indication there's 1 bit flipped in bit 4 and an even number of bits flipped, I can tell me that I must have had 2 bits flipped in this message, right? So if there's any error in the individual check bits and no error indicated in the overall parity, that tells me we had a double bit flip and we're uncorrectable. And your computer running that old memory with a sec-dead code in it will actually throw a double bit error and your program will crash and you'll have to restart it. And you should probably go out and buy a new memory chip, right? What if there were no P0? We would think P4 itself was flipped. Get a little bit into the weeds here. Hamming 7, 4, and 8, 4 code 4 data bits. 8 is a power of 2, 2 to the 3rd, right? So hamming 15, 11, and 16, 11 code 11 data bits. That's the next power of 3, 2 to the 4th, right? Hamming 31, 26, and 32, 26 code 26 data bits. Again, 32 is 2 to the 5th, right? 2 to the 5th, we take 32. We take actually 31, subtract 5, we get 26. We take 15, we subtract 4, we get 11. If we had a hamming distance of n comma d, where n is some number, right? 1 less than the power of 2, hamming of 511, right? So 31 is power of 5, 64 is power of 6, 128, 256, 512 is the power of 9, 2 to the 9th. So that would be a hamming distance. A hamming message would have 511, comma 502, because there would be 9 parity bits in that message, okay? So the message contains P parity bits, however many parity bits there are in that power of 2, and M equals N minus P data bits. If N is a power of 2, then it contains P plus 1 parity bits, in other words, the full code bits. So if I had 511 or 512, that would be a hamming distance of 4. It would be protecting still 502 bits worth of data, but we'd have then 9 plus 1 for a total of 10 check bits. I'm not going to dig into this today. It gets complicated, and I've thrown a lot at you already. Just to know that there are partial truncated hamming codes. I can go down here to this hamming calculator, and I can tell it I want to do a hamming 3126. And if I don't give it the full thing, it will add zeros to the back end of it, pad it out, right? But I can also just truncate it when I get to those zeros. I don't even have to transmit those. By the time I get to that boundary, when I get that next power of 2, whatever the length of the message is, I just assume it's padded with zeros after that. So I don't have to type in all the data. And of course, we've talked about before about how memory has that 127, whatever it was, 120, 127, 128, 120 parity. It's a nice, 128 is a nice power of 2. We've truncated it. So we've got, our data bits. If n equals 2 to the power of p, we assume it includes the parity 0 bit. If we have a bit string and we've got the overall parity bit included, we know that 13 bits must be at least 8 parity bits. The parity number of parity bits is 4. We got an overall parity bit. So that would be actually a Hamming 13, 8, 4 code. Not going to go into this. 7264, 7263. So if someone says I'll give you a message that is coded Hamming 7263, the numbers don't add up. I'm not going to go into the details on that because it's not that important. Well, they specified blah, blah, blah. Okay, we're going to do a decoding exercise now in class. So I'm going to ask you to tell me what the next step is. Okay, so the first step is encoded message is 12 bits long. I've said right here, this is Hamming 12, 8. 12, yeah, ignore this anyhow. So 12 minus 8 is 4. Since we're already longer than 8 bits, we need to have our 3 parity bits. Right, so this is Hamming 12, 8, 3. There is no P0 bit in the front. So we check our ones. Even or odd? Even. So the ones are okay. How about the twos? Now find the twos bits. Again, this is 1, 2, 3. So there's a 1 there, right? 4. Is the twos bit on in the fours place? No. Does 4 represent is 1, 0, 0. 5 represent is 1, 0, 1. 6. 1, 2, 3, 4, 5. 6 is a 1. 7 is a 1. 8. That bit's not on. 9. That bit's not on. 10. The bit is on, right? So how many bits do we have turned on in the twos place? 0, 1, 1, 1, 1, 0. Even number. Okay. Fours. 1, 2, 3, 4. Well, now it's easy to count. We just take these 4 right here. Great. That's even. But you notice out here, we have to actually go out here. 1, 2, 3, 4, 5, 6, 7. It's these 4 bits here. This is actually 8, 9, 10, 11, and this is 12. So this is actually covered by the 4s bit again, right? And the 8th bit is starting at bit number 8, 10100 is even. So that's okay. We chop off the parity, X those out, and this is the message that we originally sent. Let's try to code that 1110100. I get 10101101101. Okay, there we go. 1101. Oh, I did something wrong. Ignore me. Pretend you didn't see that. Decoding exercise. This message here will decode to 01011010 with 1 corrected error. How? We start with our encoded message. First bit number is 1. I'm just using this X to indicate that there's no overall parity, and I'm going to try to do that in the course here. When I have a message with no overall parity, I'll just put an X in that place to indicate that it's not there. So we count the 1s bits. 1, 3, 5, 7, 9, 11. We get 4 1s. There's no errors. We look at the 2s. How many bits we got? Again, there's 0, 0. Skip these two, count these two. We've got an error there, don't we? Yes? That's a 3. That's odd. So there's an error in the 2's bits. Here's the 4's bits. 1, 2, 3, 4, 5, 6, and 7. So 0, 1, 1, 1. Error there? Yes. So there's an error in the 4's bits. Now we check the 8's. And again, we start at bit number 8, 9, 10, 11 until we get up to 15. That's even. So where is the error? 2 plus 4. Bit number 6 is flipped. Okay. So we need to flip that bit and then strip our parity. And the mirror that we decode out of that message is 0, 1, 0, 1, 1, 0, 1, 0. Whereas if we didn't check our parity, we would have thought it was 1, 1, 1, 1, 0, 1, 0, right? Decoding exercise 3. Here's an encoded message, and actually I've got an error in one of the parity bits that I've introduced. Because you can have a parity bit flip. So we decode this one. Here's our encoded message. We check this one has an overall parity. You know what? Because I didn't put an X on the front, so this has an overall parity on it. And that says is 1, 2, 3, 4, 5, 6, 7. Tells me there's a single bit flipped. Check the 1s. 1, 2, 3, 4. It's okay. Check the 2s. 1, 2, 3. There's an error, right? Check the 4s. Looks okay. Check the 8s. Looks okay. Column with the error is 2s. It's the only one that's got an error. So we flip the 2's parity bit. I have a one-off error. This should be moved over one space. Should be pointing to this X. And so we decode the message just by stripping off the parity bits, and we don't have to flip any bits in their message stream. Okay. First bit is 0, 7 is odd, 4 is even, 3 is odd, 2 is even, 2 is even. Error is the 2's parity bit. Okay. I do intend to have a small homework, but I didn't get it put together. Forgot to do that. On doing Hamming encoding. And of course, we've got a wonderful way to do it simple and straightforward. I want you to try it on your own first and then go ahead and run it through this coder and see if you get the same answer. So I'll go ahead and give you the code. What I'm going to ask you to do is take your ending digits of your WSUID and code those using Hamming code. Okay, and then see what you get. Plug it into here. So, for instance, if my WSUID ends with a 9, which is 1001, is the 4 bits. And if I go to encode that with a Hamming 7-4, I'm going to get 00111001. If I encode it with a Hamming 8-4, I'm going to get an extra 1 on the front because there were 3 1s in there. Okay, so I'm going to ask you to try coding a number. We'll just get for randomization. Here's examples on YouTube. And so this is Hamming code explained with just wordless. You play some cute music in the background and you try to figure out what that music is if you're interested, but it doesn't matter. Or here's a professor that is doing it's been removed. Okay. Well, I guess we're not using that one again. Okay. So decoding exercise. So I guess we'll have to do our own decoding exercise video. Hey, maybe that'll be a good assignment. Anyhow, so that is Hamming codes. I'm going to ask if there's any questions about coding with Hamming. We can do on the whiteboard if you'd like to. You want to try it? How many people say yes? How many people say, I am bored, stiff, get me the heck out of here. This Hemming code is dull as dirt, right? So again, the point of this is a basis step, right? We're going to start doing RAID algorithms next. We're going to start looking at how we protect data on customer data in a massive storage device. Then we're going to see about how we protect data as we're transmitting it from Voyager spacecraft million miles away outside the orbit of the how many miles away outside the orbit of the solar system completely, right? It's out in interstellar space, and it's still transmitting data to the Earth. And the data is getting lots of errors in it, but they have a coding system on there that allows us to recover from just tons and tons of errors in that error encoding. It's called the convolutional code and the Viterbi algorithm. We'll go through that later in the semester. But all about how do we protect our data as we transmit it. That's what this course is about. It's still not too late to drop if you don't care how we protect our data. But again, this is a corner of the computer business that is critically important. It has to work. If you're a cloud provider, you need to know how this works. If you're a cloud user, you don't care. You just put your data out there. You assume the cloud provider has done the right thing, right? If you have a home computer, you don't care. If it crashes, you just lost your data. You don't care at all, right? No, you prefer to put your data on the cloud to store it, right? But there's so if you have data that's precious to you that you don't want to lose, you want to find ways to protect it. That's what this course is about. Okay. Let's see. What else do we need to talk about? We don't have anything about project teams in this class yet, do we? We should start forming those. And we could do it with the Hemming code. Make people decode messages of their teammates. So what we do have out here is the homework. The integrity contract, ASCII to hex. Again, the integrity contract is not due until Tuesday at midnight. So I think there's several people that have been like putting this off, but do try to get to that as soon as possible, get that filled in. That is a School of Computing requirement, not this class requirement. They want people to make sure they understand what our policy is and share that they do understand that. And then finally, attendance. We can have some fun here with attendance. So let's see how bad these questions are. Again, this is a attendance quiz. If you get every single answer wrong, it doesn't matter. We can go ahead and go through these at the end. And this is a Hamming distance metric, is question 2. Flipping one string to another. Hamming distance 5, how many errors can you correct? Sorry, I'll bring it back up. 807,871. There's a Boeing airplane in the middle of this, 787. Yeah.